So how is it that we know that the redox reactions that I had just shown were actually redox reactions and not something else like a double displacement reaction or a acid-base reaction or whatever? And the answer to that is we need to look at changes of, or I'm sorry, charges of elements in the reaction. We're going to look at the oxidation state or the oxidation number of those different elements in a compound. This comes from section 4.2 in our textbook. Oxidation state, by the way, is just the charge of a species with no sharing of electrons at all. And so there are some rules that are laid out in your textbook. And the first rule is that the sum of the compound has to equal 0. So for example, in the case of the ammonium dichromate video, this compound has no charge associated with it whatsoever. Likewise, the Cr2O3 has no charge, or the water has no charge. So the total charge of all the elements in the compound must equal 0. In particular, we'll look at the last one, the water. Typically, we're going to see H as being a +1, and the charge of the oxygen being a -2. And so if we do 2 times the 1 plus the -2 of the oxygen, we're going to get a total charge of all of the elements being equal to 0. All right. The second rule is that the charge of an element is equal to 0. The example that we saw in the dichromate volcano is we were looking at N2, and there is no charge on the nitrogen element here. The total charge is equal to 0. The third is that the charge of a monatomic ion is equal to the charge that is given. And so the best example I have of this is back when we were looking at acid-base chemistry. If we looked at HCl reacting with water, we found that it split up and made H plus and it made Cl minus. So the charge obviously on the hydrogen here is a +1 and the charge on the chloride is a -1. The next rule, 4, is that the most electronegative element gets the negative charge. And so when I'm going to take a look at some different kinds of molecules here, but if I were looking at, say, a molecule of SO2, and if I were to draw the Lewis structure for that, I would draw it such that it looked like this. Right, so this is sulfur dioxide. And the most electronegative element here is the oxygen element instead of the sulfur. And what that's telling me is that this electronegative oxygen is going to get all of the electrons that are associated with it. And so those two oxygens, this oxygen here is getting 8 electrons. This oxygen here is getting 8 electrons, which means that this sulfur is getting a mere 2 electrons. There is no sharing of these electrons at all. It is a matter of the most electronegative element getting the electrons. So what this means is that since oxygen has a valence of 6, because it's in the 16th column or the 6th column, depending on how you're counting that, we're going to take the valence and we're going to add to, or let me subtract, the number of electrons associated with it. So we end up with a -2 for the oxygen. On the other hand, the sulfur, it has a valence of 6 as well because it sits right below oxygen. I can't get that 6 there, right? And we're going to subtract from that the 2 electrons that it has, and that's going to leave us with a charge of, sorry about that, plus 4, right? So the oxidation state, or the oxidation number of sulfur in this case, is a plus 4. That of the oxygen is a minus 2. Take a second here and tell me if you can come up with the oxidation numbers for each of the elements in H2S. Put me on pause here, right? And when you come back, you should recognize that the symbol for, or the Lewis structure for H2S looks like this. We're going to have a couple of electrons here. The most electronegative element here, by the way, is the sulfur. And so the sulfur is going to get all of those electrons. And so the sulfur in this case is a minus 2, and the hydrogen is a plus 1 charge. Okay, so that takes us to rule number 5, which is that hydrogen is usually a plus 1, whereas oxygen is usually a minus 2. There are certainly exceptions to this rule, and those exceptions come into play when we're looking at rule number 4, which talks about the most electronegative elements getting the electrons. Imagine if hydrogen were combined with, say, something like sodium, right? If we put sodium connected to hydrogen, the more electronegative element here is the hydrogen, and so it's going to get all of those electrons. And since hydrogen has a valence of 1, we subtract the 2 electrons that are in the bond, we end up with a minus 1 charge for the hydrogen. The sodium has a valence of 1, and it has 0 electrons around it, and so it ends up with a plus 1. So hydrogen is actually a minus 1 in that case. Oxygen, there's a couple places where sometimes we see it not being a negative 2. Besides its elemental state, and one of those examples is hydrogen peroxide, H2O2. And so if we were to draw a Lewis structure for that, we would get that, right? And so this oxygen is going to get all of those electrons, this oxygen is going to get those electrons, but who gets the electrons in the middle where there is a bond, right? That bond represents 2 electrons, so I'm going to take out those 2 electrons and I'll put those back in as 2 single electrons. Okay, so which oxygen gets those electrons? They're going to be shared, right? So we end up getting a line down the middle. So this oxygen gets the 2 electrons on top, 2 electrons on the bottom, 2 electrons in the bond to the hydrogen. That's 6 electrons plus the 1 electron in the middle. So we end up with a 6 minus a 7, 6 valence, 7 electrons around it, equaling a negative 1. So the oxygen has a negative 1 charge. The hydrogen in this case still a plus 1 because it's 1 minus 0. Okay, and you can see now that the total charge of the H2O2 is equal to 0. The other place where we might see a difference is in maybe something like the compound OF2, right? So in that case, which element is more electronegative? And the answer is the fluorine. So if the fluorine is more electronegative, it's going to get any electrons that are in that shared bond. And so the fluorine is going to have a valence of 7. We're going to subtract the 8 electrons that are going to be around it. So the fluorine becomes a minus 1. And if we must have a neutral charge on this, then the fluorines are going to each be a minus 1, so a grand total of minus 2. Therefore, the oxygen is going to be a plus 2. And we'll work out some of these problems here in a bit. The very last rule here, rule number 6, is that the metal gets a positive charge. And the reason for this, of course, is that metals are not electronegative, so they get the electrons taken away from them. So in example here, chromium 3 oxide, When we take a look at the oxygen here, the oxygen we said was going to be a -2. There are 3 oxygens here, so that's a grand total of -6. We do know that the total sum of all of the elemental charges has to be equal to 0. If that's the case, that means that the chromiums must be adding in a +6, which means each chromium in this case must be a +3. So I have the individual charges up top, and then the total charges of all of the elements down here at the bottom. And that's another way to solve these problems. I think I'll stop at that point.